Hello, this is Mrs. Schroeder, coming back to see you today and talk about gas laws in Chapter 12. Our objective today is to cover Boyle's Law, Charles' Law, and Gay-Lussac's Law. So gases, as we learned before, are affected by pressure. We try pushing on the syringe and we can squeeze those particles together. Temperature will change how gas particles act, and volume of the container also changes how gases behave. So gases we have to describe by the properties that we can measure. A gas at a certain temperature and a certain pressure behaves one way. A gas at a higher pressure behaves a different way. So we use the following variables. P always stands for pressure. It could be in any of those units we talked about last time. V always stands for volume. So capital V stands for volume occupied by the gas. T stands for temperature. Notice it must be in Kelvin. If you forget, you add 273 plus the degrees Celsius to get to Kelvin. You have to use Kelvin when you're talking about gas laws, or your laws won't work. And then a small n stands for number of moles of the gas. And we're gonna always have to know what those are. In 1662, Robert Boyle was experimenting with gases and came up with the following relationship. He found that if his pressure and volume change, if he changes one, the other would change. And by doing this experiment many times, he was able to determine that the pressure and volume, when multiplied together, always equal a constant. Now that constant would be different for different systems. If I have a container of helium or a container of chlorine gas, it might be a different constant, but if it's the same gas, the same system, I have a balloon full of helium. If I squeeze that balloon, the pressure times the volume is going to be constant no matter what. So he was able to determine the actual mathematical relationship, which is what we're going to use in this class, that the first set of conditions, P1, V1, is going to be equal to the second set of conditions, P2, V2. And the subscript 1 versus subscript 2 just stands for which condition, the initial or the final condition. And this picture illustrates what happens when pressure and volume change. If you see the first piston in A, gas molecules are far apart, they're spread out to fill the whole cylinder. Now when this cylinder squeezes down and decreases in volume, you see my gas particles get closer together. When they get closer together, they also get closer to the walls. They hit the walls more often, and as we learned last time, more collisions equals more pressure. So when the walls are closer, they're going to hit the walls more often, and you're going to increase the pressure. So gas pressure will increase. Now we actually see this inverse relationship, which you guys are going to prove in lab. But what we find is that as pressure increases, the volume is actually going down. Again, if I squeeze something together, I can squeeze it so small that the volume will actually decrease into a very small volume. So when we're solving gas problems, make sure you write this down. This is what we're going to use for all our gas problems, this whole chapter. First, I'm going to just gather my information. I have to write down what I'm given in the problem, whether it's pressure, volume. It could be temperature also, if it's giving me temperatures that change. It could be an N that changes. Whatever those initial information is, gather it, write it down, take it out of the word problem. Second step, rearrange the gas law to solve for the unknown variable, whatever the unknown variable might be. If I had P1 and I'm trying to find P1, I know that P1 times V1 is equal to P2 times V2. So how do I solve for it? I can do this. Divide both sides by V1, and I get P1 is equal to P2 times V2 divided by V1. That's rearranging the gas law to solve for my unknown. The third step is just to insert the quantities into the equation. So whatever these quantities are right here, you're going to put them into the equation wherever they go. So let's try one. If you open your book to page 425 and you look at your book, so take a moment, pause the video and open your book up and look at question number 1. It says a sample of oxygen has a volume of 150 mils at a pressure of 0.947 atmospheres. What is the volume of the gas at the pressure of 1 atmosphere? The temperature remains constant. So, for those of you who don't like to write things down, write them down. Logan, write them down. Pressure 1. If I look at that, I have to figure out which is my first condition. And it really doesn't matter which one you keep as pressure 1 and pressure 2. Just make sure they're both written down as the same thing. So pressure 1 I'm going to say is 0.947 atmospheres. That's my first condition. And my volume is 150 mils. Okay, at the second condition, 1.00, I've changed the pressure. I've increased it slightly. And my volume 2 is what I'm trying to find. So I'm going to rearrange my equation to solve for V2. So remember I had P1 times V1 equals P2 times V2. To get V2 by itself, I divide both sides by P2. And that's simply a way to do it. Now before I put the numbers in, I want you to think for a moment. Do you think the volume should go up or should go down? Think about Boyle's law. My pressure went up, so my volume should go. If you said down, you're correct. So, put your numbers in. V2 equals 0.947 times 150 divided by 1.00, and I get 142.0 mils. And that's my final volume for V2. So pressure went up, volume went down. That worked out nicely. Okay, next one. Charles' law. He found, this is about 100 years after Boyle, and he was, again, trying to discover some things about gases. He found that expanding a gas, or heating a gas, makes it expand. Cooling a gas makes it contract. This is something that you've seen before if you've ever gone out into the garage and tried to ride your bike when it's cold out. The tires are probably flat. Or you go get the basketball out of the garage and it's flat because it's cold in the garage. So cooling something down makes it contract. It goes flat. But actually Charles was looking at volume and temperature. So he had a container that wasn't a fixed volume. It could actually, the container could actually change in size also. He found that volume over temperature is a constant. So mathematically, again, rearranging just like we did with Boyle's law, two conditions, V1, but now it's V1 over T1, not times T1. Whenever you have temperature, temperature's in the bottom. So V1 over T1 is V2 over T2. Remember, temperature must be in Kelvin. It is a direct relationship, so if temperature is going up, volume is going up. It's expanding. If it goes down, temperature goes down, volume goes down, it contracts. So open your books to page 428. We're going to try another one. So I want you to take a moment and make sure you're writing these down so you have an example to look at. Brandon, that means you too. So if I'm looking at page 428, question number 1 says that helium gas in a balloon occupies 2.5 liters at 300 Kelvin. The balloon is dipped into liquid nitrogen that's at a temperature of 80 degrees Kelvin. What's the final volume of helium in the balloon when the temperature changes? So think about it. What are we going to do here? Well, my volume 1, my first set of conditions, 2.5 liters and 300 Kelvin. Volume 2 is what I'm trying to find. I put a question mark there. My temperature of liquid nitrogen is 80 Kelvin. So if you can see, my temperature went down, the volume should do what? So if you said go down, you're correct. So now I'm going to rearrange my equation. I still had V1 over T1, but now I'm going to multiply it by T2. I took my T1 from the bottom and I multiplied it to the top. So, put your numbers in, 2.5 liters times 80 Kelvin divided by 300 Kelvin. And I get the answer is 0.67 liters is what the volume 2 stand is when I'm done. And it makes sense. Volume went from 2.5 down to 0.67. My temperature went down drastically also. Last law is Gay-Lussac. I know it looks like Gay-Lussac. It's Gay-Lussac is the way it's pronounced. A French guy pronounced his name differently. But he was experimenting with pressure and temperature, and he found, just like Charles, that temperature has a big effect on the pressure of the gas. So if the volume remains constant, he found that when the temperature increases, the pressure increases. And same thing is true. If the temperature goes down, pressure goes down. And he found this constant direct relationship. So, his law can be written as P1 over T1 equals P2 over T2. Again, temperature has to be in Kelvin. If I look at my practice problem on page 431 of your textbook, I would look at the first one. Question number 1 says at 122 degrees Celsius, the pressure of a sample of nitrogen is 1.07 atmospheres. What will the pressure be at 205, assuming constant volume? Okay, so when I go to write out what I know my pressure is 1.07 atmospheres. I know my temperature is 122 degrees Celsius. Before I do anything else, I know I have to add 273 to get 395 K. I'm trying to find P2, and it told me that T2 was 205 degrees Celsius. Again, add 273, and I have 478 K. That's a 7, not a 2. Okay. So when I go to use Gay-Lussac's law, I'm trying to find P2 right here. So when I rearrange, this T2 is going to go to the top. Multiply both sides by T2, and I get P1 over T1 times T2. And again, think before you start the problem. My pressure or my temperature went up, so my pressure should go. Figure it out? Yes, it should go up also. So put my numbers in, 1.07 times T2, which is 478, divided by 395, and I get my pressure 2 of 1.29 atmospheres. And that's P2. So, tomorrow in class we'll do some more practice problems with all 3 of these types of problems. And we'll stop there for this section for now. We'll continue later. But I want you to think about those 3 laws. Try to come up with some examples on your own. Look around you. See if you can get an example of something for each one of those laws that would illustrate in your head and help you keep track of what actually changes when temperature, pressure, or volume of a gas changes. So look around tonight, think about it, come in with some ideas of what would illustrate each of those laws.